All right. Hey, Honors Chemistry. So I wanted to make sure I provide to you some notes in my absence on quantifying energy. Just make sure you know that I have a little typo in the beginning. In these notes, as I mentioned in class, we are going to be able to come up with two equations that I could use to calculate how much energy is going into a system. There are going to be situations that I'll see. If I have 50 grams of water here and I have 100 grams of water here and I'm changing the temperature, remember delta T means change in temperature. And the way that we're going to get change in temperature, I'm going to write it again. Delta T is going to be T final minus T initial. So an example of changing the temperature by 10 degrees Celsius would be going from, 10 degrees Celsius to 20 degrees Celsius. 10 degrees Celsius to 20 degrees Celsius. So if I take 50 grams of water and change it from 10 to 20, which gives me a delta T of 10 degrees, and I have 100 grams of water and I change it from 10 to 20, how much heat is involved? Well, we're going to see that heat, Q, is directly proportional to mass. Okay? But what if I had the same mass? What if I had the same mass and instead of me changing the temperature by 10 degrees Celsius, I change it by 30 degrees Celsius. So I'm going from 10 degrees Celsius to 40 degrees Celsius. If I have the same mass and I'm changing its temperature, that amount of heat is going to also be proportional to the change in temperature. And combining these both, if I have more water and I change the temperature by 30 degrees Celsius, let's say I'm going from 10 degrees Celsius to 40 degrees Celsius, if I change the mass and the temperature, I'm going to have a relationship of heat that corresponds to mass and delta T, or change in temperature. And so we're going to put that equation together, and you're going to see that I'm going to have heat for a mass and a change in temperature, and then heat for what happens if temperature doesn't change. Okay? So let's go to the bottom here now. To consider quantifying energy associated with temperature changes, we have to think about energy changes, which is going to be Q. Temperature changes, delta T is T final minus T initial, and the number of particles, or mass, M. Well, the quantity that I want, or will maybe be given, is going to be my energy, Q. I want a quantity of Q. A quantity that I'll be given, or that I'll have, will be mass in M, and this is going to be in grams. And I'm going to have some relationship that's going to relate energy to mass. Another thing to keep in mind is that another relationship that happens is that energy per particle is associated with temperature. Remember, hotter particles move faster. That means they have more thermal energy. And I'm not going to write it here, but slower particles are colder, they have less thermal energy. And so I'm going to have a relationship that relates energy and mass, which is delta T. Okay? And I'm making this table here because eventually this table is going to be my equation. It's going to say something like Q is going to be equal to delta T times M, and I'm going to need one more factor in here. I'm going to need a constant, which is C. And so I'm going to see that energy is going to be equal to C times delta T times M, where C and we're going to write this down and move this up a little bit. C tells us a certain mass will require a certain energy to change the temperature by 1 degree Celsius. So C tells us a certain mass will require a certain energy to change the temperature of a mass by 1 degree Celsius. This has a special term. This is known as the specific heat capacity, C. Okay? So, why did I put this here? I have a quantity that I want, a quantity that I will have. I'll have a certain mass that's like up here. And I have some relationships that I need to help me go from one quantity to the other. One relationship will be a change in temperature, because we know if I heat up things, if I have more or less things, I'll get a change in temperature. And I need one more relationship that's going to help me go from mass and change in temperature to energy, and that's specific heat capacity, C. Okay? So I have some quantity that's going to relate change in temperature to mass, and this is going to be a constant. All right, so I have the beginnings of an equation. Q is going to be equal to C times delta T times mass. This C relates change in temperature and mass to energy. All right, now what happens, let's go to the next page. What happens if I don't have a change in temperature? Well, a quantity that I will want and have is energy. Okay. And a quantity that I will have will be mass, M, in grams. I'm going to need a relationship that relates quantity of energy to mass in grams. And there's no delta T. Temp does not change. So I cannot use delta T in phase change energy calculation. If I do, I'm going to get 0. And then if I multiply, divide, add, or subtract 0, it messes up my calculations. If I multiply by 0, I'm going to get 0. If I divide by 0, I'll end up getting an undefined number. So I cannot use delta T. I need another relationship that's going to help me relate energy to mass of my phase change. And that relationship is going to be called H phase. Okay? And so we're going to write down what this is. H phase is the heat required for a phase change. It's a constant. This is a constant. And so I'll see energy is going to be equal to H times my mass in grams. So heat required for a phase change. Later on in chemistry or in advanced courses in chemistry, we call this the enthalpy H. It's a fancy term. And it's different for different phase changes. So there's going to be an H for melting, there's going to be an H for boiling, there's going to be an H for freezing, there's going to be an H for condensing. By the way, the H for boiling and melting are going to be the same. H for melting and freezing are going to be the same. And and we'll just leave it at that. Melting and freezing requires the same magnitude of energy. Boiling and condensing requires the same magnitude of energy. So now putting this together, we're seeing that we have two equations that are forming that you're going to have to know how to use, and we're going to do examples of. I have energy is going to be equal to mass and delta T times C, this quantity that relates change in temperature and mass to energy. And I have energy is equal to energy of phase times mass. Putting this together, we have two equations, and there are going to be some constants and things that go with them. So the first one is the equation associated with temperature changes. There's going to be, I like to put it as Q is equal to MC delta T, where Q is the heat energy, and that is in units of joules. This is new to us. It is unit of energy. M is the mass in grams. The specific heat capacity, and we're going to use for water, is in joules per degree Celsius times gram. This is the units. Joules over degrees Celsius times grams. Sometimes you can see it as joules over degrees Celsius times grams. What this means is I have a specific amount of energy of joules per degree Celsius per gram. What this says, this specific heat capacity says, this substance or whatever I'm talking about requires a certain amount of energy to change the temperature by 1 degree Celsius by this mass of 1 gram. And then, of course, the change in temperature, if I need to calculate it, will be final temperature minus initial temperature. Note about delta T, it's negative for cooling. Delta T is positive for heating. Doesn't that make sense? I would lower or be lower in temperature. I'm going to be losing energy if I'm cooling, and I'm going to be gaining energy if I'm heating. So delta T is going to end up being negative if I'm cooling, and so energy is going to be leaving the system. Delta T is going to be positive if I'm heating. I'm going to be gaining energy. Energy is going to be going into the system. And then we have two values for C that we are going to use in our examples later. The specific heat capacity of liquid water is 4.18 joules per grams degree Celsius. I just plugged it in for C here. The specific heat capacity for solid water is 2.1 joules per grams degree Celsius. Again, I plugged it in for here, and you have to be told what phase. Later on, if we use other substances or other phases like a gas, I will have to tell you what C is. All right, and so that's our first equation. Our last equation is now what happens if I don't have a temperature change. It's going to be Q is equal to H times M. Or sometimes I like to write it as Q is equal to M times H. Same thing. And don't forget that this little dot is like a product dot. Okay, so it's multiplying. Where Q is the energy or the phase energy or the energy required for the phase change, which is in joules. M is the mass in grams, and then H is the heat of the phase change, and we also call that enthalpy, and that's in joules per gram, J over G. What this is saying is this phase change requires a certain amount of energy per gram. And so for melting or freezing, HF requires, for water, for melting and freezing, it requires 334 joules per grams. Let me tell you, for melting, it's going to be positive 334 joules per gram. For freezing, it's going to be equal to negative 334 joules per gram. Freezing, I'm losing energy. And then the same idea for heat evaporation, evaporating condensation of water, that requires 2,260 joules per gram. For evaporation or boiling, that's going to be positive 2,260 joules per gram. For condensing, that's going to be negative 2,260 joules per gram. So what this is saying is I will require 2,260 joules to evaporate or boil 1 gram of water. Seems like a lot, but it is. What this one's saying is I need to remove 2,260 joules for every gram to condense it. Positive means add energy. Negative means remove energy. Okay, so I'm going to end these video notes for right now on these definitions and equations. In the next video, we are going to be doing example problems in these notes where we get a chance to read, analyze, and interpret questions and use these equations.